Optical lithography is the current workhorse of chip manufacturing processes. It is, however, limited by the wavelength of light employed, approximately half of the wavelength. One way to increase the resolution of features is to reduce the wavelength down to extreme ultraviolet. However, at such small wavelengths, all solids, liquids, and gases absorb at 13.5 nanometers. So the system needs to be under vacuum, leading to higher cost than the optics used and added complexities. Another possible way to push beyond the realm of optical lithography is to use electrons. However, techniques such as scanning electron beam lithography are expensive and are serial processes. To write an entire chip using a scanning electron beam would take hours, which is a far cry from the minutes of exposure that mass-based systems use. This has prevented the widespread implementation of e-beam systems. The Laboratory of Optical Nanotechnologies at the University of Utah is currently working on a novel technique to circumvent the resolution limit of optical nanolithography. One such approach for fabrication of diffraction-limited features over large areas is called patterning via optical saturable transformations, or POST. POST exploits unique combinations of spectrally selective reversible and irreversible photochemical transitions between two states A and B to achieve deep subwavelength resolution at low light intensities. The organic photochromic molecule used in POST is a direalethene derivative named BTE. Direalethenes are a well-known photochromic compound that are thermally stable and fatigue resistant. The transition between the two isomers is induced by the photoirradiation of UV or visible wavelengths. In POST, a thin film of organic photochromic molecules are thermally deposited onto the surface of a substrate. The molecules are then excited uniformly with lambda-1, rendering it reactive. Next, patterns of intensity minima of lambda-2 are used for photoswitching molecules from a state B into a state A with distinct spectral properties. Following a saturated photoswitch into state A, only at the nodal point is the molecule confined to state B, which is then locked in to write the nanostructure. Since the beams affecting the saturable transition are inevitably diffraction limited, the breaking of the diffraction barrier is a result of the saturation that is left out at the zero intensity node. Translating the sample, the process can be repeated to create complex geometries in a dot matrix fashion. Finally, due to the solubility rate difference between state A and state B can be selectively removed in a polar solvent, leaving behind subwavelength features that can later serve as a resist for pattern transfer into the underlying substrate. In the future, low-cost nanostructure processing will become more widely applied. For example, in light trapping used in photovoltaics, biosensors, and optoelectronic components.